Show in the language of my people, the Dakota, means water is life. This phrase was first thrust onto the national stage in 2016 during protests against an oil pipeline that was slated to run right next to local indigenous communities. While that phrase became a rally cry for their movement, I believe it captures the essence of my research quite well. Water is life, and for some, their livelihoods are in danger. Over the next 25 years, 1/4 of the US is expected to face moderate to extreme water scarcity, with an extreme case being about 2 weeks per year where current water supply does not meet demand. That means taps, plumbing, and irrigation would all run dry. This future is only certain if we continue to use our current water sources, with 70% coming from surface water and 29% coming from fresh groundwater extraction. That last 1% encapsulates all of the current desalination capabilities in the US. In order to provide water to future generations, expanding this is going to be key. And this is where my research comes in. When we think about salty water sources, the ocean usually comes to mind first. But if you consider the 60% of the US population that does not live near a coast, we have to look elsewhere. Fortunately, it's been well documented that salty groundwater sources are quite abundant in the continental United States. The technology I research, electrodialysis, is commonly used to desalinate salty groundwater. It is a membrane-based approach that uses an applied voltage to drive ion removal. This applied voltage causes dissolved ions in the salty water to move and become trapped in alternating channels. This creates potable water and concentrated brine. The energy demand of electrodialysis depends on 2 factors of a salty groundwater well: depth and temperature. In the US, depths of salty groundwater wells range from 50 feet to 1,500 feet, and temperatures range from 5 degrees Celsius to 50 degrees Celsius. Deeper wells take more energy to pump up to the surface, while warmer wells speed up that ion movement and allow for a more efficient process. My research aims to create a model that considers these 2 factors and predicts the specific energy demand of electrodialysis for a specific salty groundwater well. This will be a useful tool going forward for determining where we can make electrodialysis the most sustainable process possible. Water is life, but I feel like this phrase can also be used in reverse. We must be fluid when approaching problems caused by climate change. My research into the temperature dependence of electrodialysis will allow us to use salty groundwater sources more sustainably and effectively going forward. Thank you.